I've probably quoted it before. When he was asked, what's the worst form of government? So Churchill was asked, what's the worst form of government? What's the best form of government? And he said, well, democracy is the worst form of government except for all the others, right? So in other words, there is no perfect, right? So what's the best language? C is the worst language except for all the others. Python's the worst language except for all the others, right? So there is no perfect language. There is no perfection at all because it all comes down to humans and preference, right? Yep, we're good. All right. So thankfully, CodeSpaces is working here. Let me see. Is it too small for? Yeah, it's too small. I can't even see it up there. So let's go ahead and pick up where we last left off here. We'd done a difference between a create book and an init book here. The create book actually creates it for you by calling malloc and setting up the memory for it. And then init book doesn't do that. You're already given a book that exists already, and then it sets up all the other ancillary stuff. We had a book to string, print book, free book, etc. And then our final example here was that I created a book calling create book, Venus plus X, and then we printed the book and then we freed it up. I'm going to go ahead and run Valgrind on this. I've already compiled it to show you that there are no memory leaks at all. Okay, there are no errors, there are no memory leaks. All the code is to perfection right now. Right? What I want to do now is I want to show you what happens when you aren't careful and you mix up creating a book versus initializing a book. So let's go ahead and create an array, just a static array, right, of books, right? And I'll make it of size 3, okay? And then I'm going to go through and initialize each one of those things. So books of 0, I'll call create book here, right? Okay? So give me another book. I just finished up reading Madameo to my kid, my son, by Jacques. Is that how you spell Jacques? C? Like, okay, there, that looks better. Jacques, and then what's his name? Anybody read Redwall? Say what? Brian, thank you. Like that? I'm pretty sure it was 1989. And after the third book of fighting big giant rats, big giant cats, big giant foxes, it gets old. So I don't think we're going to continue on the series there. Right? Right. So create another book here. Anybody want to offer up what they're reading right now? Not a lot of readers. No? I'm okay, but Butlerian Jihad. Is that how you, I don't know. Brian Herbert. I have no idea when he published it. Let's just go, I think it was 2000s. And then there's a second author there. And it's turning out to be not so great. But I've never not finished a book before, so. Books, so 1 or 2, I'll go ahead and create book. I don't know. Oh, Emma Jane Austen. Okay, Emma Jane Austen. What? Emma. Emma. Emma Jane, is it? Okay, that's what I was going to say. Jane Austen. Jane Austen. Austen. A-N, thank you. And Emma wasn't by one of the Brontes then. Okay, thank you. All right, I, Robot by Isaac Asimov. All right, I don't know, 1852, whatever, right? And I've never read it, so I'll just go ahead and assume it's good since it's a classic. Right? So I've got 3 books here, okay? Now, could I free these up? Let's try. Free books sub 0. There we go. Free, and I won't bother printing them because I know that works, but when you go to do your hack and design your own test cases, this is about what you like. Choose choose data that's meaningful to you, or that it is clear that it's a test. For example, in your lab yesterday, all we did was test 001, test 002, test 003. It doesn't have to be real data. All right. So let's go ahead and compile this again. G demo and book.o. I didn't change anything there, so that should be good. And already I'm getting an error. All right. Why? Books of 0, what is that? Right. Well, technically, what is books? Books is an array. In other words, how do we represent an array in C? With a pointer. It's a book star. However, books sub 0, in other words, one of them, is a regular old book. Right? Can you pass in other words, it's not a pointer. Can I free something that's not a pointer? Not really. It's going to try to interpret that as a bunch of numbers and then jump to that memory address and try to free up that memory address. And that memory address is not even valid, may not belong to me, etc. So the compiler is being a good enough compiler here that it's not even letting me do this. Okay. There's an incompatible type here. Okay. So let's think about lines 23 through 25 first. Right. So create book returns a pointer. Right. But books of 0 is a book. How do I take the thing that has been returned as a pointer and change it into a regular variable so I can assign it to books of 0? So we need to dereference whatever create book returns in order to assign it. Right? In other words, what we want to do is we want to take that book star and we want to make it into a regular old book. Why? Because that's what's on the left-hand side. So how do I dereference something? Star, star, and star. All of those errors are now going to go away. Those first 3 errors are now going to go away. So let's go ahead and try to compile that again. All right, there we go. So those first 3 errors are gone. Okay. Ampersand is just the opposite. That's the referencing operator. Right. So I can't do this. Right. So I need to do the opposite. Right? What do I do with each one of these? It's just a regular book, right? And so I need to get the memory address of that thing. I need to go in the opposite direction, right? Maybe. Let's try it. Ampersand, ampersand, ampersand. There. GCC. Well, first of all, is that going to, I mean, now it's just a warning, right? I wonder if I run this, hopefully I'm going to get a stack smashing event, right? Why is that? Yes, or double free or corruption, right? Something happened there. So why? What happened? This was a static array, right? Where is it allocated? On the stack. It's in the stack frame. Do I need to free it at all? No. In fact, I shouldn't, because that's a stack smashing event, right? And that's leading to this double free or corruption. Okay? So definitely not. Yeah, go ahead.
What exactly happens during this stack smashing event?
So you've got memory, right? In fact, we can look at the visualization here again. iCloud. We've got plenty of time. We're not going to get to recursion today. Where's the call? Memory stack. There we go. All right. So there's the memory stack, right? The program code is loaded up first. Then you've got global variables and static content. This entire stack belongs to your program, right? And as you call function, say main, right? Main calls average, average calls sum. You are creating stack frame upon stack frame upon stack frame. When you return, each one of these pops off, pops off, pops off. But then later on in the program, you're going to call more functions, right? So more stack frames get created. Then they get popped off, they pop off more, right? It's always building up, and it's always being torn down, right? What if I said, okay, well, I don't need this memory right here anymore, right? And I tried to free it. Would I ever be able to call another function to use that memory? No. So it's basically like I'm deleting myself, right? I'm deleting the memory that was given to me in order to operate. And so the operating system says, no, you can't do that, or that's a bad thing. So abort, right? Or some sort of an error. So those 3 lines that I just got rid of, that's definitely bad, because we would be freeing up memory that belongs to us that we still need. So I'm going to go ahead and get rid of that. I didn't need to do that anyway, right? Because, oops, there we go. Because it's a static array. It's in the stack frame. It's going to get cleaned up when that stack frame gets popped up. Or more accurately, it's going to be reused next time I use that stack frame, that area. Right? So let's go ahead and compile this again. Remember, I'm using the G flag Y because I want to debug and I want a clean report from Valgrind telling me where any potential memory leaks occurred. So Valgrind a.out. Right. Oops. Valgrind a.out. There we go. So now I do have 3 errors from 3 different contexts. Right? Why? Well, I count. How many books did you count there? 1, 2, 3. Strong hint there. So let's come up here to the first one. Right? There are 1 blocks indirectly lost in create book, then in init book, malloc on line 27. Right? And then if you go down, you'll find that there's another one lost on line 26 and another one lost on line 25. Okay? So now think about this in terms of visualization. I don't have it here set up, unfortunately, but we can get rid of that. But there are actually 2 books. Let's just isolate this one line right here. Books of 0 and create book. Let's separate it out so that we're looking at it line by line. What does create book do? It returns a pointer. Book star PTR to book. Right? So I'm actually calling create book. That's 1 book right there. It's on the stack, on the heap. Why? Because I called malloc for it. But what about this thing right here? That's another book. Right? It's on the stack. Right? This is on the stack. So when I go to do something like this, where I say books sub 0 is equal to PTR to book, well, again, that didn't compile. What do I have to do? I have to dereference it to change it into a regular old book so that each one of those things could be copied into the other book. What happened to this guy up here that's still in the heap? Memory loss, memory leak. Right? I've got my static book, which the dynamically allocated book was now just copied into it, but this guy is still remaining over here. Right? What would I have to do to make this successful? I would then have to, after assigning it, I would have to free PTR to book. Right? There. I would have to do that over and over and over again because using it like this is a memory leak. I am ignoring the thing that was dynamically created, copying it over into the statically created thing, and I'm losing access to that pointer. So let's rethink this. If I have an array like this, should I be calling something that dynamically creates a duplicate array, basically? Probably not. What were the 2 creational patterns that we just looked at? One of them is create book that creates a brand new book on the heap, right? One of them is a init book that a book already exists, and so it will just initialize its values. Does the book already exist in this instance? Yes, 3 of them do. So it was wrong to call create book. Instead, we should have called init book. Right? And which book is it? Book sub 0. We'll come back to that. And then all of this stuff right here. Right, there we go. Right. Yep, exactly. It hangs around because it's in memory. It's in the it's located in the heap. So let's go ahead and get rid of all of this and rethink all of these. So init book of books of 1, comma, and then all this stuff. Good, good, good. And then init book. This is where that trick of using not square bracket notes, the way of editing things using block selection mode instead. Oh, and I need books, sorry. There we go. And no create book, but Emma by Jane Austen. There we go. All right. Now let's see if there's a memory leak. GCC. Oops. Yep. We're back to not being able to compile. Let's once again review. Books is an array. It's a book pointer. Books of 0, one of them, like I'm trying to do right here, is just a regular old book. But what does init book expect? It expects a book star, a pointer. So let's put an ampersand in front of that. Now it's kind of weird because you are accessing an individual member here, but that is a regular old thing, regular old integer, regular old double, regular old book. Right? You need a pointer to it, so you can go ahead and put a pointer in front of it. This is already a pointer, right? Because it's pointing to the beginning of an array. But you don't have to point to this first one. If I've got 5 books here, right? Here's my first pointer. I can point it to the second one. I can point it to the third one. I can point it to the fourth one. Just like we did when we did a substring, right? I didn't want to point it to the first character. I wanted to point it to the third character or the fourth character and start copying or concatenating from there. So undo, undo, undo. There we go. And we're back to normal here. This should compile. Yeah, it does. It should run. We are not doing anything with it yet. But let's go ahead and ask Valgrind. Is there a memory leak here? There is going to be, but now it's 9 errors from 9 contexts. 3 books. Let's take a look at what the definition of a book is. Oh, sorry. There we go. I count 1, 2, 3 dynamically allocated strings. There's a strong hint as to what that leak is. Remember that we have a free method here, right? That frees the book. Be careful, right? It frees the title, it frees the first name and the last name, but then it goes on to free B. Is that going to work with our static array? No, because again, you can't free a static array. So you might need yet another version of the free book here. You always have to be reminding yourself of where is this thing located? Is it located in the stack? Is it located in the heap? Right? So in order to memory manage everything. These 3 I'm not even going to bother fixing because they're all in the main, right? They all go away. But I do want to introduce some more convenience functions here, right? So I want to print all 3 of those books. Well, I could do something like this over here in demo. I could say print book. Why did I put an ampersand in front of it? To make it into a pointer, right? Print book, print book, print book. 1, 2, 3. There we go. TCC. And now it actually prints something out. There we go. Everything is good, right? Right? Good. Right? But then I have to do this all over the place, right? I could write, say, a for loop to do this instead, right? For int I equals 0, I is less than 3. In fact, I'm going to put that into a variable. Int n is equal to 3. I plus plus. Then I can go ahead and print all of these books. Right? Right? Oh, wait, I. There we go. CCC. And it works just as well. You know what? That's probably so useful. Maybe I should put it into a function. So one of them is not just print book, but another one would be print books. We didn't already do that, did we? No, we did in the other section. Right? So what's the difference between having a pointer to 1 book versus having a pointer to 5 books? Well, I put an S there. Right? What else does the function need to be told if there are multiple books? How many there are? Int n. So anytime you see this pattern in C, where you're taking a pointer and the size of that thing, that tells you that by convention that's an array. Technically, 1 pointer can be treated as an array of size 1, right? It's just one thing, right? But I'm not going to pass in the fact that n is equal to 1 here, right? It's just print book. And of course, I still need to do my documentation, and that would actually clarify that there are n, this is expected to be an array, and that there are n of them in that array. So let's move this over to, or not move it, but let's copy this over here and implement it. And for that, I'm just going to steal this code right here. There we go. I don't need to declare n, I'm given it, right? And print book there, and then return. And now I don't need to worry about doing it manually. I'll just go ahead and print books books, and then 3. Why didn't I have to put, is that right? Let me ask that. No. Books is a what again? It's a pointer. I would be dereferencing it. I would actually be getting books of 0, right? Jump to the location that you're pointing right now at these 5 books. I've jumped to that location. What do you now have? That 1 book, right? Is that right? That's the memory address of the memory address, right? Books is already a book star. There's that memory address being stored somewhere in memory. I want the memory address of the variable storing that memory address, right? And that's definitely wrong because that memory address probably doesn't exist. Right? All right. Oh, actually, it exists. It's just that it's not going to get me what I want, right? Oh yeah. What else do we need to do? I've changed the books now, so I need to recompile my library over here. Uh-oh. They call it something different? Oh, duh, I should have done this. Instead of just B, there are several of them. Books. There, that's a little bit better. And then do them all together, and yay, it's still working. Okay. So, again, you really need to be careful on what you have a memory address, where something is actually being stored, et cetera, et cetera. That's about all as sophisticated as we're going to get. If you're looking to go the extra mile, definitely read my textbook and definitely watch video, I think 11.3, because there are alternatives. Right? So here's what we've basically covered, right? And I'm just going to go over this visually here. Now instead of a person, we've got a student here. That's the example I use in the book. And when I create an array of students, right here, like we've done with an array of books or whatever, right? Then it ends up creating something that looks like this. Right? We've got rosters of 0, which is say 40 bytes. Right after that, somewhere in memory, is the next one, rosters of 1, then rosters of 2. In other words, it's being allocated all as one contiguous thing in memory. Okay? And each one of these, when you access them, is a regular old structure. Okay? And that's how we've been using this stuff. There is an alternative. You can have an array of pointers. There we go. In other words, a star star. Now, normally when we've seen star star before, we're thinking about 2-dimensional arrays because you have an array of pointers. Each one of those pointers points to a row. But since these are one structure, it's a row of size 1. Okay? And when you do it like this, it could be all over the place in memory because you're initializing each one separately. Create the first one, right? Well, that ends up being over here. Create the second one. That ends up over being here somewhere. Maybe they're contiguous, maybe they're not. Right? I drew it like this so that it'd be all over the place. That leads to kind of fragmentation, right? I mean, yes, this is nice because everything is dynamically allocated. It all exists on the heap, right? You've got more than enough room. You've got pointers and all the advantages that pointers gives you. But it's very, very fragmented, right? In fact, even only getting 40 bytes here, it might end up giving you an entire page, an entire kilobyte, meaning that you are wasting 900 bytes. So instead of having 400 bytes like we did up here for 10 students, now we might have 10K, right? And that's bad, right? Yeah.
Is this how you defragments?
That's the same defragging your hard drive, right? That's the same concept, but on an actual larger scale. I'm not sure if that's even an issue with like the bubblegum ones anymore. The NVMs, what are they called? Those, the hard drives that are on a stick of bubblegum. What are they called? SSD. Well, yeah, they're SSD, but they're
NVMe.
NVMe or NVM or whatever it is, whatever they are. But certainly on older mechanical hard drives, you wanted everything to be close together because you've got mechanical stuff moving. Like if one part of the file is on this, you have to move all the way over here to get the second part, move all the way over here to get the third part. That mechanical action is, of course, very slowing you down big time. Right? And it was even worse on the big giant tape decks in the 50s and 60s, right? And you do not want fragmented memory at all, right? Not so much an issue, on RAM or whatever, but yeah, you don't want this. So there are certain advantages to this and disadvantages to this. There are certain advantages to this and disadvantages to this. And that's why I prefer, when I do stuff, the hybrid approach. The best of both worlds. Right? So it's an array of pointers, right? But each one of those pointers points to a contiguously allocated array of structures. Right? For example, what if I needed to sort these things? What if I needed to move this student down here and this student up there because I was ordering them by their last names, first names, right? I needed to sort them. Now, in the first option here, that would mean that I take all of this memory here and I move it down here. I take all this memory in here and I move it up here. Not that big of a deal for 40 bytes, but if these structures are much larger, then it starts to become a big deal. If you're in an embedded system, certainly even 40 bytes is a concern. But here, if I wanted to swap two students, what would I have to do? Just take their 2 pointers and move them around, right? This one points to that one, and now this one points to that one, and you've moved them around. You've swapped them. But I still want contiguous allocation because I don't want it fragmented all over the place. Now I've got the perfect setup, right? Things get super trippy though, right? Because now you've got pointers to pointers, right? You need to make sure that everything is allocated correctly, et cetera, et cetera. If you're looking for an example of this, just go back to Lab 6, right, where we provided the code that allocated all the pixels. Right? We didn't actually allocate them all over the place. We didn't actually even do a 2-dimensional array. Right? That's what this would have done. This is what we've been teaching you so far. Right? This is what we did to actually load up the image. All the pixels, the first row, the second row, the third row, the fourth row, it was all flattened out. And then the pointers pointed to this first segment of this entire array. And then the second row pointed to this next segment. The third row pointed to the next segment. And that's how we did it, so that it was something like this. Right? And at the time, we didn't draw attention to it or anything. But this is what we were doing because it's far more efficient. Again, don't worry about doing it this way. If you want to, go ahead and explore it and see what it looks like. But things get trippy because now you've got pointers to pointers, everything. And what if this is a 2-dimensional array of students? I don't know why you'd want to do that. Anyway, but then you would have pointers to pointers to pointers. Right? You can have 10 stars. Right? Now you've got pointers to pointers to pointers to pointers to pointers to pointers. It's all over the place. Right? So again, if you are interested in this, watch video 11.3. I go through an entire animation of how this gets allocated. Right? But as far as we're concerned, we're going to keep it simple, right? And those are all the methods or the functions that I wanted to show you. Okay. All right. Let's see. Any questions on that so far? Yeah.
So that would be in the middle of the program when
Sure.
you were declaring that static.
This right here.
Array, like books. Could you kind of explain like how that, I guess, kind of works out in the
That is like this, except that it's not dynamic, right? It's just creating n of them.
Oh, that's right. Because it's all back.
Yep. I'm not calling malloc here because it's just. Oh, sorry. It's just 3 of them right here. Right? So it exists in the stack. They're all contiguous, one after the other. If I had done this instead, here, in fact, let's look at this. So here we go. Books as a pointer, and then dynamically allocated it, right, is equal to book star malloc size of book times, I want 3 of them. I'll just hard code that. There we go. Then, now how would I call each one of these in nits, right? It'd still be the same. Because I am dereferencing it, right? And then I am passing it in. Right? So yeah, there we go. Let me go ahead and grab both of these and There we go. I could still compile this just fine and still run it just fine. But now because each one of these is dynamically allocated, I can free them this way with non-zero offset. Yeah, okay. So no, I can't free it this way. So let me get rid of that. Instead, how would I free it? I would free books there. But I would still have a memory leak because the title, the first name, and the last name have not been cleaned up. Right? Just this one contiguous array has been cleaned up. Right? So again, keep it simple. Right? I'm going to go ahead and get rid of that and get rid of this, but restore the original. There. Okay. All right. Well, let me move so I don't lose it, demo into book demo, and then we'll post that later today here. And then I will, copy book demo back to demo.c. All right, so then let's reopen this, and I'm going to go ahead and get rid of everything here. And I'm going to give you a challenge. Oops, come on. There, get rid of that, get rid of that. There, now we're all clean. Right? So here's my challenge. Print out a countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ... 1, blast off. But no loops. In other words, no for loops, while loops, or do while loops. Right? And no hard coding. Yeah, you could just go printf 10, end the line. No cheating. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. In fact, one of the, no, you can't do that. One of the things that some faculty are opposed to auto grading because, they could just cheat by printing out the expected output. They could run it once to see the expected output and then just cut and paste that and put it into a print statement. Like, you still check the code, right? People have tried that before, and no, it's obvious that it's wrong, right? Right. So no loops, no hard coding. All right. Well, what does that leave us that we've learned so far? Variables, sure. Right. Print statements, so yes, we got to use that. So input, output. Conditional statements, yeah, right? Because if it were a 0, instead I could just print blast off, right? Okay. So I could put in a variable here, n is equal to 10, and then printf, if n is equal to 0, then I could say printf blast off, end the line. Otherwise, maybe I want to print the actual value because it's a countdown, right? %d, end the line, n, right? That doesn't really get me anywhere, right? If I were to run this, it would be hard-coded to 10. It's not moving. It's not making a change, right? Yeah?
Could you maybe create a function right through?
So we still have access to functions, right? So let me go ahead and create a function here. I don't know what the return type is going to be. We might want to wait on that. And I've got a countdown, because that's what it is. And then it takes an integer n. Right? And now let's move this stuff up there. Right? So if you gave me 0, then I'll print blast off and return. Otherwise, I'll print out 10. This is still hard coding if I did something like this, right? Countdown of n, countdown of n minus 1, right? This is still hard coding it or putting it into a while loop, right? 1, 2, 3, right? 2, 3, 4. I'm not going to write it all, but let's go ahead and look what indeed that function is working. Oh no, countdown. Ta, 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 ta. There we go. Let's run it. There you go. 10, 9. Okay, so yeah. But again, this is hard coding it. Yeah. Okay. Count down, right? Because I just printed 10, right? Now I want to print 9. So how could I forward that to another call to countdown? N minus 1. Or minus minus. CCC. Let's see if this works. Hey, did it. Countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Wait a second, a function calling itself? Right? Now some of you have probably seen this before, so what do we call that? Recursion. Hey Google, I don't use Google, I use DuckDuckGo. Try to use DuckDuckGo, right? Don't use Chrome. Get on the Firefox. Get back on the Firefox bandwagon, I should say. Anyway, unless you enjoy ads. So let's ask Google, what is recursion? Oh, come on. Okay, fine. Recursion. So what is recursion? Maybe I misspelled it. There we go. Oh, what is recursion? There's been this little joke on the Google engine for a long time. You know, programming humor again, right? What is recursion? It's self-reference, right? So let's look at some other things that are recursive, right? Now I'll go to DuckDuckGo. Mandelbrot set. You might not have seen seen the name before, but you've probably seen pictures like this. If we just look at an image here, right? There's the Mandelbrot set. Right? That's called a fractal. A fractal is a mathematical object that is self-recursive, or that is referenceable, right? Or here's an even clearer way of seeing it: the Sierpinski triangle, however you pronounce it. The triangle. Come on, there we go. Let's just look at the triangle, not the 3D triangle. But here we go. That's a good illustration right there. It's recursive. Here's the following operation: take an equilateral triangle and remove the middle equilateral triangle. Recurse. Repeat that for each one of the resulting 3 equilateral triangles. This is equilateral, right? Okay. All right. Do that again. Do that again. Do that again. Right? And it turns out that these have really weird mathematical properties. For example, a cube, just a regular cube, is 3-dimensional. Right? Now, project that down onto 2 dimensions. What do you have? A square. Right? Project that down onto 1 dimension. What do you have? A line. Project that down onto 0 dimensions, and you have a point. Right? Project that cube up to 4 dimensions, and what do you have? Oh, it's in the Marvel movies, Tesseract, exactly. Right? A 4-dimensional cube. Right? But these fractals have dimension that is in between those. Right? So you can have instead of having a 2-dimensional, the Sierpinski triangle here is not 2-dimensional. It's actually like 1.78 dimension, right? It's a fractal. It's a fraction of a dimension. That's where we get this name. Right? And so it's a different mathematical definition of what a dimension is, right? So that's all in, math. You've probably seen this one as well, the Fibonacci sequence, right? Let's look at the Wikipedia version of it, right? Where you've got a function that is defined in terms of itself. So what is the nth Fibonacci number? Well, it's equal to the one previous to it, and then plus the 2 previous to it. So in other words, if you start out with 0 and 1, well, what's the Fibonacci of 2? Well, it's 0 plus 1, which is 1. What is Fibonacci of 3? It is 1 plus 1, which is 2. What is Fibonacci of 4? It is Fibonacci of 2 plus Fibonacci of 3, which is 3. Right? And then 5, 8, 13, ... Right? It's a recursive function, a function that is defined in terms of itself. Except for these 2 guys up here. Right? Can it go on forever? No, you need a starting point. Right? So let's come back over here and visualize this now. Now that I've got my blast off code, let's actually put this in here and see what it looks like. Right? Yeah. There we go. So we enter the countdown. I've got countdown sub n, which receives a value of 10. Right? There we go. So it's not equal to 0. It gets printed out. And I won't bother printing it, looking up there. But then we call countdown of n minus 1. What is about to happen? Predict. I'm about to call this function on itself again, right? What happens when a function calls a function? A new stack frame appears. There we go. So I've got a stack frame for 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Dot, dot, dot. Come on. There, 3. I'm only on 3. 2, 1, 0. Right? Now we're going to print blast off here. And did it yet? Nope. One more step. There we go, blast off. Now look at that stack. Right? What's going to happen as I return back from each one of those functions? It's growing downward, but just flip the screen upside down if you want to, in your mind. Right? It's going to end up popping these off. Right? So there, I'm back to 1. Next. Now I'm back to 2. Right? Next. Right? Each one of these gets popped off the top. So in other words, to accomplish this challenge without a loop, oops, I don't want that. Without a loop, I basically had to abuse the stack to do it. Right? Now there are other ways of doing this, tail recursion, where you're not abusing the stack as much. In fact, we're going to look at ways of alleviating the need to use the stack at all with some examples here probably next time. But that's recursion. When a function calls itself. Now be careful. Right? So what if I forgot my... Actually, no, here. What if I started this at -5? Right? Now predict what's going to happen here. -5, you come into this function. What happens? It's not equal to 0. You don't print blast off. So we print -5 and do what? -6. So here is an example of runaway recursion. Right? So it is technically an infinite loop, but we're eventually going to reach an end really, really quick. Why? Stack space is limited, exactly. Stack. Eventually, when you get down to 261,000 some calls, right, you've exceeded your stack space and now you've overflowed it. Now you have stack overflow. Right? This is one of the reasons that certain organizations, NASA, have banned recursion in any of their code. Right? Their style guides say, no, you can't do this because of the risks of runaway recursion. Right? A for loop is way more straightforward. A for loop doesn't have a risk of running away like this. Right? I could have also gotten my, this is called a base case, where you stop the recursion at some point. And if you don't have that, then, or if you screw it up accidentally, right? If, I don't know, if it's greater than 0, then it'll never catch it, right? How do I screw it up? I'm trying to think of how to screw it up so that it's meaningful. It's so straightforward, I can't screw it up, right? In any case, right? I probably need another base case here, right? So for example, if n is less than 0, right, then I need to do something else. If it's 0, I'll still blast off. If it's greater than 0, then of course I'll continue my countdown here. But what should I do if it's negative? Printf, error, or whatever, and then return. Right? Or bad input or whatever. In fact, now I'm thinking, well, wait a second, this is a void function. Maybe I should make that into an int function to return an error code. Now I don't have this runaway stack problem here. It's just an error. Okay? So yes, recursion is the answer. Now, granted, this was a toy challenge here. Right? I could have achieved this with a while loop. I could have achieved this with a for loop. The idea here is that you can use recursion to simulate a loop. There are certain languages out there that either don't have loops or that really discourage them. They're called functional languages. Scheme, Haskell, Lisp, right? These are a different programming paradigm. Instead of a procedural style like this, execute this, execute this, execute this, they are functional. Function calls function, calls function, calls function. In fact, you don't even have any variables other than parameter variables, right? And parameter variables really aren't variables. Right? There's no int n in those languages, or you're discouraged from doing that. Right? Instead, you set up all these functions as a bunch of dominoes, and then you get it all started by pushing the first domino over, and then they all fall together and give you an answer. Right? Those are called functional languages. And if you ever have to program in one, good luck to you, right? Kind of, yeah. Now, there are people that would say functional, functional all day long. They're all functional, including students that I've met. The argument for functional has always been, in my mind, that you really have to be 100% mathematically oriented, right? Because only math people think in category theory and think in functions all the time. Humans, most of us at least, think in procedural style all the time. We do 1, 2, 3, 4. This is a process. It's an algorithm. Step 1, step 2, step 3. That's how we live our lives. And I'd prefer to program how I usually think rather than having to force myself into a mathematical mindset all the time. Right? And that's my argument against functional programming languages, but whatever. Right? My undergrad was in math, so who am I to speak? All right, any questions? Otherwise, we'll continue there. Yeah, go ahead. It is returning. Right? Where is it returning? It's returning down here. Right? So this is an if-else else. So this is all mutually exclusive. Exactly one of these three things happens. Regardless of which one happens, it returns. Now, your question would be, when it gets back, so suppose that it does recurse, then eventually this function will be done executing and return. Where does it return? Right here in the program. Well, what's next? A return statement. Right. Does that answer it? Okay. Yeah.
Yeah, I have a question about when you know when to use recursion and when to use a loop. Where's some
So when we get into the details on Friday with an example, people will argue that there are things that lend themselves naturally to recursion. I would say, yeah, I mean, the code is super simple for some very limited use cases. But every single one of those use cases, you can write an equivalent loop. Just like if you have a for loop, you can rewrite it as a while loop. You have a while loop, you can rewrite it as a for loop. If you've got recursion, you can rewrite it as a loop, right? And simulate the recursion. And what we're actually going to look at is a technique called memoization. It's not me mispronouncing it or having a stroke. It's not memorization, it's memoization, right? Memoization is where you do use recursion, but you try to cut out the repeated operations by saving them into a table and then looking them up. So we're going to look at a hybrid approach to this. You can always program away any recursion, right? In fact, when some languages came out, like Fortran, it didn't support recursion at all. If you had a function calling itself, it would not compile or it would not run, right? So recursion is something that's added to languages or is there from the beginning, but it's not necessary. Right? You never have to write it. I generally don't unless, okay, yeah, it's much easier to just do it like this. Again, it forces you to think of it in recursive terms. All right, I'll see you on Friday and we'll look at that example.